Hey guys, so the next part of our unit here is about waves, and we're going to talk about waves. We're going to talk about different parts of waves, what different parts of waves are called. We are going to talk about the speed of a wave, and we're going to learn the wave speed equation, and then we'll solve some problems using the wave speed equation. So our target here is to be able to apply the relationship among wave speed, frequency, wavelength, and solve some problems with it. So waves are kind of a little different than a lot of things that we've talked about so far. Most of the things that we've talked about in physics up until this point have been a thing that's moving. And a wave is more like a movement through a thing, right? Waves require what's called a medium. A medium is something that the wave moves through. If you think about sound waves, move through the air. If you didn't have any air, you couldn't have any sound waves moving through it, right? So, the wave requires a thing to move through. Ocean waves move through the water. Other waves move through other things, right? There are two different kinds of waves that we're going to talk about that are important for us to understand the difference between. One of them is called a transverse wave. A transverse wave is the kind of wave that goes up and down. It's your kind of ocean wave that you think of, an up and down sort of wave. Looks like a sine curve or a cosine curve, depending on how you're thinking about it. The other kind of wave is what's called a longitudinal wave. A longitudinal wave is more like what's called a compression wave, where different parts of the medium will maybe have different densities, and that densification moves along the medium, right? Sound waves are longitudinal waves. So let's go ahead and let's talk about some different parts of these waves and what they're called. All right, both transverse and longitudinal waves have some different parts we need to be aware of. And here you can see a diagram of a transverse wave. And you can see some different parts of it that are labeled there. You can see the high point in the wave, the highest point, is labeled as called a crest. So the high point in a wave is called a crest. And you can similarly see the low point is called a trough. So, a transverse wave will have a crest and a trough. And the distance between two crests you see labeled in the diagram there is called the wavelength. The wavelength doesn't have to be the distance between two crests. It could be the distance between two troughs. You see that also labeled in the diagram. But it could be the distance between any point on the wave and the same corresponding point on the next wave, right? So what you see there in the diagram is more than one wave. One wave is like the wavelength, right? So crest to crest, it's more than just one wavelength. But any two corresponding parts on the wave, the distance between them will be called the wavelength, right? You can also see labeled on there the amplitude. The amplitude of the wave is not necessarily the distance between the trough and the crest. It's the distance between kind of the equilibrium point and the crest, or the equilibrium point and the trough. So those are some important words for us to know, parts of a transverse wave. A longitudinal wave also has some parts for us to be aware of. You can see the diagram here of a longitudinal wave, and you can see the parts where it is, bunched up and dense are called compressions. And then the space in between there, where it's less bunched up and dense, is called a rarefaction, right? So compressions and rarefactions. And you can also see the wavelength labeled in there. The wavelength would be the distance between two compressions, or the distance between two rarefactions, or really the distance between any two corresponding parts in the wave, right? So some important parts of the longitudinal wave there. You saw in those diagrams labeled what's called the wavelength. Okay, and the wavelength is an important thing for us to understand here. The wavelength, we're going to do math with it. You can see the wavelength, the variable we use for wavelength is the Greek letter lambda. Looks kind of like an upside down Y or something like that, right? So lambda stands for the wavelength. And wavelength is literally a length, so we measure it in units of length. We'll measure it in meters, or for some waves we might measure it in centimeters or millimeters or even nanometers or something, right? So wavelength is measured in units of length, of distance. We're going to see in a minute a relationship between the wavelength of a wave and its frequency. So let's talk about frequency for 1 second. We talked about frequency in one of the last few lessons, but let's think again about period and frequency. Okay, the period is how much time it takes for something to happen. When we're talking about waves, the period is how much time it takes for one wavelength to happen. The frequency is how many of those wavelengths happen each second. Period is measured in seconds and frequency is measured in hertz. You can look at the diagram here and you can see 20 waves happen in that diagram. 20 waves happen in 1 second. So because 20 waves happen in 1 second, we say the frequency is 20 hertz, right? But because period and frequency are reciprocals of each other, the period of each wavelength in there, you can see one wave marked on that diagram. The period is going to be 1/20th of a second. Because 20 of them happen in a second, the period is 1/20th of a second, or 0.05 seconds. So period and frequency and wavelength, and there is a relationship between the frequency and the wavelength of a wave, and it's tied to the wave's speed. This is what we call the wave's speed. So here you can see an equation that says V equals lambda times f. That means that the speed of the wave is equal to the wavelength of the wave times the frequency of the wave. And we're going to use this equation to solve some problems. So let's go and take a look at that. All right, here's the kind of problem we might end up seeing. It says a piano string tuned to middle C vibrates with a frequency of 262 hertz. There's a frequency. 262 hertz. Assuming the speed of sound in air is 343 meters per second, there's a speed. Find the wavelength of the sound waves. So they're asking us, find the wavelength. Okay, so we know two of the three things in this equation. We're looking for the third one, so let's put the numbers in there and solve. V is 343. Lambda, we don't know. That's what they asked us to find. And the frequency is 262. So I will go ahead and divide to solve the equation. 343 divided by 262. And we're going to need three significant figures there, so I'm going to say 1.31. 1.31. And then what units are we going to put on that wavelength? We're going to put meters. One more example here. It says the speed of all electromagnetic waves is 3.0 times 10 to the 8th meters per second. Calculate the wavelength if a radio wave with a frequency of 88.0 megahertz. Okay, so it tells me that the speed of the wave, V, is 3.0 times 10 to the 8th meters per second. And it tells me that its frequency is 88.0 megahertz. So the frequency, but I don't want to work in megahertz. I want to work in hertz. So, if you go and you look up the prefix mega, mega means 10 to the 6th power. So I'm going to put 88.0 times 10 to the 6th hertz. And they ask us to find the wavelength. Okay, so we've got two of the three numbers in the equation. Let's go ahead and put them into the equation and solve. So V is 3.0 times 10 to the 8th Lambda is what we're looking for, and F is 88.0 times 10 to the 8th. So we will go ahead and divide to solve that. So 3.0 times 10 to the 8th divided by 88.0 times 10 to the, oh, I'm sorry, that's 10 to the 6th. 6th. All right, and we need what, 2 significant figures? So I get 3.4. And by the way, this is a radio wave that's, you know, about the same kind of frequency that a radio station would have, right? If you think about your radio dial, your FM 88 on your FM radio dial would be 88 megahertz, right? So how long would that radio wave be? It would be 3.4 meters, which is, I don't know, 10, 11 feet. So the length of that radio wave that you're listening to on your radio is, you know, 3.4 meters. Pretty neat, huh? All right, there is a little bit about some different parts of the waves and about the wave speed equation. We did a couple examples there. Hopefully that helps us to be able to apply the relationship among wave speed, frequency, and the wavelength to solve some problems. So until next time.